Now I'll start with the next most wanted topic, which is how computer vision works, how machines see images. Okay, so in artificial intelligence, there is a particular concept which relates to the which take cares of the visual aspect of the problems, which is computer vision. Okay, before we get to computer vision, you need to know how actually is an image constructed. An image is completely made of pixels, which are considered to be the fundamental units of an image. Like each and every pixel has a corresponding numerical value between 0 to 255. We will get to know more in detail from the next slide. The illusion of sight. You know how humans see objects or shapes in context actually be processed instantly, right? Like we do not require to think of something to be able to identify it. We can almost instantly identify what an object is or what a shape is and what particular context is. But when it comes to machines, it doesn't work the same way as in humans or any other living being. Machines only see numbers, and specifically only zeros and ones, only the binary bits, which are called as bits, 0 and 1. So what actually happens is that when when there is an image which we need to have it processed, each and every pixels will have a corresponding numerical values, right? So what actually happens is that a 2D matrix of pixel values will be built. A matrix is nothing but a combination of rows and columns. Horizontal lines are rows, and the vertical ones are columns. So and each and every color pixel is going to contain for suppose we are going to take the concept called as RGB, red green blue, which is a category which we will have in the form of uh, round box RGB, where we are going to have color encodings for numerical value encodings for each and every different type of colors. For example, we have the red color which will be represented in the form of 255, 0, 0. And remember this, each and every value will have only values between 0 and 255. Okay? And the data volume. As I have mentioned before, an image will be corresponded to a numerical representation of 2D matrix, right? And the representation can be in the form of any number of rows and any number of columns. Like for suppose if you have a 3 by 3 matrix, then you are going to have nine values within it. In the same way, if there is 224 by 224 matrix, then it is going to contain 1,50,528 values. The core computer vision pipeline: image, preprocess, extract, predict, and act. First, we are going to consider the image, which will be the input, right? And the input will be taken for the pre-processing stage, where the image will be resized and the data will be normalized. And we will have the extraction stage, where the model is going to identify the facial landmarks according to the problem which we are going to solve. And next is the prediction, where the model is going to calculate the probabilities based on the problem. It is also based on the problem, and the probabilities are going to be between 0 to 100%. Based on how accurate the model thinks its prediction is, it is going to give a corresponding probability value to that part. Like for suppose if you consider object detection, and there is an image which contains a car and a human, and it identifies a car, and the estimate which it is giving, the accuracy which it thinks is like maybe around 75% or 80% based on the performance of the model. Act. Here, this is a generalized CV pipeline which can work for various different types of processes like object detection or classification, etc. Here, the action is dependent on the problem which we are going to solve. Based on that, that will be the action and also the prediction. The core, the inbuilt techniques which we use will be different based on the problem, but the uh, general overview is the same. Image, input, pre-process, extract, predict, and act. Pre-processing. How an image is actually pre-processed. Let's consider the image to be a raw input. It will be considered as a raw input, right? Because that's what which we are going to input to the model. The image will be resized so that it will have a constant values between a particular number of rows and columns. Let's consider we take 224 by 224 here, and the values will be normalized. This will improve the mathematical stability. As I have mentioned before, the value of each and every pixel is 0 to 255, right? That will be scaled down to 0 and 1, so that each and every value will be between 0 and 1. Next is the augmentation stage. Augmentation is really important when it comes to computer vision. The reason for it is because we cannot consider the object within the image to be only in that way, right? Even when the image is flipped, rotated, or cropped, or some noise is added, like the image is not clearly visible, the model should be able to accurately predict even in these conditions. So intentionally, we are going to create these type of scenarios where we are going to have the data of the same image in flipped, rotated, cropped, and also noise added, where the image clarity will be reduced and such. The deep learning shift. Previously, before the current era, where the process is completely automated, previously humans had to identify manually. They had to identify the edges, the corners, the textures manually, which was very rigid, unscalable. Unscalable in the sense, for suppose if there are thousands, tens of thousands, or hundreds of thousands of images, then it isn't viable for humans to finish it. Even if we take a lot of manpower, it would take a lot of time, right? And it also broke easily in real world conditions. In modern era, due to the development of convolution neural networks, the paradigm has completely shifted from manual to automatic. Convolution neural networks is a type of neural networks which has been developed more specifically for the visual type of problems. Okay, here as you can see, the input will go through the convolution layer one, and it will go to the pooling next for the layer two, and the number of layers is dependent on how we design the architecture. Okay, and it at last goes for the fully connected layer and goes for and an output will be predicted. Okay. And before that, I would actually make you know about what a neural networks is. Artificial neural networks, which we have an artificial intelligence, is mimicked based on the brain, where neurons are interconnected to each other. In the same way, we have the neural networks, where artificial neural networks, where convolutional neural networks is a type of it, where we are going to have multiple neural neurons connected to each other in multiple layers, and the activation of these neurons is dependent on the activation function which we are using. So these activation functions are just mathematical formulations which we use based on the problem which we are going to solve. There are various different types of activation functions which are used to activate the neurons, like tanh, sigmoid, relu, leaky relu, etc. So, due to the development of the convolution neural networks, the complete manual process has been converted from hard-coded rules to dynamic pattern recognition. Inside the CNN, how actually a CNN is architecture. First, as I have mentioned, like convolutional neural networks. We need to know what a convolution is. Convolution is a filter. Okay, so when an image is going to be inputted, it will pass through a filter, and these filters are going to be helpful for extracting the patterns within the images. Okay, that's what convolution works for. And how they actually do is it's completely mathematical. Based on the mathematical formulations, the convolution is going to work, and the way the filter is going to work. So, like various different types of patterns, like vertical edges or anything as such. And we have the activation. As I mentioned, convolution neural networks, it is going to have multiple set of neurons and multiple set of layers, right? So the activation of these dependent on the activation function which we are using. For suppose we have the ReLU, it is going to transform the values like the numerical values which we are going to get from the image. As I have mentioned in before, it will be converted to a 2D grid of a matrix, right? So those values will be converted based on the activation function, like f of x equal to max of 0, comma x, such that all the native values will be ignored and nonlinearity will be introduced. It will improve the accuracy of the model. And we have the pooling. Pooling is a step which is going to shrink the grid. Like, for suppose we have the matrix of the image in the form of 224 by 224. It will be converted to a value of 2 by 2 region, which is going to massively improve massively reduce the compression which is required and also improve the robustness. The hierarchical brain. So the model do not see an object. Okay, as we have talked in beforehand, it cannot see the way humans see. It detects the highly probable statistical combination of distant field textures and shapes. It is completely based on probability. It is completely based on statistical predictions. Okay, like in the layer one, for suppose within the diagram which you can see in the slide, layer one raw pixels are combined into basic edges. Layer two edges are combined into textures. Layer three textures are combined into recognizable shapes in layer N, and in that way we are going to have multiple layers. And in layer N, shapes are combined to identify objects, complete objects. So the image will be deconstructed and reconstructed. The training group. Okay, this particular training happens, repeats multiples, millions of times until the predictions align with reality, such that the accuracy of the model reaches the performance which we desire. So, for suppose while the training is undergoing, when the model is makes a prediction and outputs the probabilities based on its current state, this prediction will go for the loss calculation. Loss calculation is nothing but we are going to calculate the error, the difference between the predicted values and the real values, actual values. And based on the loss and based on the threshold which we have put, it will either go forward or it will back propagate. Back propagate in the sense the system will go back to the previous stage where the weights of the filters will be adjusted so that the error will be reduced. The weights is nothing but the importance which we are going to give to that particular numerical value. Okay, it is completely based on these weights that how the model is actually going to perform is going to be dependent on. So in back propagation, the weights of the filters will be readjusted. This process goes on multiple times. The prediction, the loss calculation, and the back propagation till the desired accuracy is achieved. The taxonomy of visual tasks. In computer vision, there are various different types of visual tasks, like classification, which means that we are going to classify an image or an object. Like for suppose we have an image where the animals needs to be classified and the vehicles needs to be classified. The cars, the bikes will be classified as vehicles. The cats or dogs within that image will be classified as animals. So that's what classification is. Object detection. Object detection is for detecting the objects which we have predefined. Like it needs to detect a car as car. So for this, for these predictions, we are actually going to use bounding boxes. These boxes will show the area of detection and also the probabilistic estimate of how how much the model thinks it is accurate to that particular object, to what it has predicted. This is mainly used in security cameras. Image segmentation. Image segmentation is used for segmenting the objects within the image, like for the road, for the car, for humans, etc. It is mainly used in autonomous driving, in self-driving cars. OCR and extraction. OCR and extraction is completely about extracting the text, the textual values from the images. Like for suppose you have an image where you need to extract the number plates from the cars or other vehicles. For that, we are going to use optical character recognition and extraction, converting the embedded visual text into raw, readable text. Advanced architectures. There are various different types of architectures which we use for computer vision. Traditional CNN, ResNet, YOLO, vision transformers. Okay, let's get to know about the mechanism of each and every architecture which we have in here. Traditional CNN use sliding mathematical filters. As I mentioned before, convolution is are these mathematical filters which are dependent on the mathematical formulation which we have uh, given to that particular filter. ResNet. ResNet, the main mechanism of ResNet is introducing skip connections. YOLO. The main mechanism of YOLO is that it processes the image in a single pass. Like it processes the entire image in a one go. Vision transformers. Vision transformers is going to work in this way. The image will be split into patches, and attention mechanism is used. Attention mechanism is nothing but focusing on the core aspects. Like for suppose you and your friend is in a shopping mall, and you are trying to find your friend in a large crowd of people. We are going to focus right. That particular concept is attention mechanism. Key advantage. Traditional CNNs are lightweight and proven feature extraction. Okay, as we have seen in before, after the manual process to has been automated right after the start of the convolution neural networks. This is what one of the main advantages of traditional CNN. Feature engineering, feature extraction. It is able to extract the features automatically, the main features. ResNet. The main advantage of ResNet is it solves vanishing gradient problems and it allows for incredibly deep networks. So it actually allows for complex problems which requires multiple hundreds of neural network layers. YOLO. The key advantage of YOLO is that it's very fast and it provides real-time object detection. Vision transformers. The key advantage of vision transformers is that global context, understanding without convolution. The reason why this is very important because the main part where it receives this particular advantage is from the attention mechanism which is used in the vision transformer. Traditional CNNs are mainly used in basic image processing. ResNet is used in complex image classification. YOLO is used in surveillance and high-speed tracking like security cameras. Vision transformers is a state-of-the-art multimodal AI. Vision transformers can be used for almost any computer vision task, like object detection, image segmentation, classification, etc. Optical character recognition, etc. It can be used for any problem which we have in computer vision. Real world architecture. Let's consider the case of a self-driving car. The main module which is going to allow this computer vision to happen is camera. The camera module, which is going to be a high-end camera module, and the other main components for the self-driving car to work is the radar and the lidar. And mainly when it comes to self-driving cars, the models are segregated. Like for suppose for lanes, for cars in the sense for vehicles, and for pedestrians in the form of for living beings. So a model will be trained for each and every type, and all these vision models, the outputs of all these vision models will be fused as a sensor fusion. Okay, all these models which we have, all the vision models which we have, will run parallelly, run simultaneously, and the outputs will be fused in the form of a sensor fusion where we have the central processing unit, and a truth map will be created. A truth map is nothing but the vision data is mathematically merged. All the merged data will be merged with the radar to build a 3D truth map. Okay, so based on this truth map, the decisions will be taken by the decision engine, whether the brake should be done, or the car should be accelerated, or it should move in a different direction, steer to a different direction. So this is how the architecture of a self-driving car. Under the hood, constraints and hardware. The real-time constraint. Systems like Tesla Autopilot must process frames in milliseconds. The delays are fatal because this is a real-world scenario where the processing should be almost real-time, right? Not almost, it should be real-time, right? So there shouldn't be any delays so that there won't be any accidents. Okay, this is one of the core aspects which should be passed through for the vehicle, for the self-driving car to work properly. Hardware resilience. The amount of computational power which requires for this to be done is a lot. There is it should be done via GPUs or specialized CPUs, which are graphic processing units or tensor processing units. Optimization funnel and deployment. Quantization. Quantization is a particular aspect which we use to reduce to reduce the size of the model so that it can run faster and minimize the accuracy loss. Okay, and for the self-driving cars, so that there won't be any issues. The model cannot be put in a remote cloud server because there might come issues where where if the cloud server doesn't work, there would then it can cause a lot of problems, right? So we are going to have a concept called as Edge AI, where it will be incorporated into a local mobile device, directly into it, so that it can work, so that it can function even more efficiently. Fragility and failures, adversarial attacks. See, even small mathematical calculated changes can completely fool a model's classification. So the model should be very robust to adversarial attacks. Environmental noise. The real world doesn't work the same way as in how we simulate within a system, right? Because there can be multiple uncertainties, like the weather can change, lightning changes, bad weather, or cluttered backgrounds. So all these needs to be taken into consideration for real-time self-driving cars. Occlusion. If key statistical features are partially hidden, the model's confidence plummets. So these type of scenarios should also be considered so that no failures can happen. The main reason, the main core flaw with the models is that it doesn't possess any logical reasoning. It is completely based on statistical predictions. It is completely based on what it has learned, the learned textures and statistical patterns. It doesn't possess any logical reasoning like us humans possess. System integration. This is one of the real-time examples. Okay. There is an example where, for suppose there is an app where you're going to capture an image of a dish and you want to search for that image in which restaurants for the dish, in which restaurants it is available. Okay. So what actually happens is that when the user uploads the image of the meal, it will go for the computer vision microservice, which classifies the exact dish. It's going to identify what that exact dish is. And afterwards, it will go for the database matching. It is going to match against whether that particular dish is available in the local restaurants or not. And it is going to return the restaurants where that particular dish is available. This is one of the real-time examples on how a computer vision application will work. Okay, so we are going to have a quick recap of what we have actually learned. The first is the pixels, which are the fundamental units of a image, which will be converted into numerical values, where it goes for the convolution layer, where we are going to have the filters, and we are going to have the features identified. There we are going to have the feature engineering and extraction, where we are going to have all the features extracted for this for the prediction for identifying the patterns within the images, and we are going to have the probabilities where where the machine where the model is going to learn the probabilities for different aspects of the images, and we are going to have the actions. The type of actions which we are going to perform is going to be dependent on the problem which we are going to solve. So there is the end-to-end reality where the first is the pixels, convolutions, features, probabilities, and actions. The future is multimodal. We already have the multimodal AI, where models can be used for various different types of tasks. Like it can, like a more, like different from the traditional models, where a specific model is created for a specific task, like for computer vision, for computer vision, for visual data, a visual model is created. For text, a large language model is created. Textual model is created. But right now we have multimodal AI, where the same model can be used for multiple tasks for the same for text, for visual type of tasks, etc. Allowing it allows AI not just label images, but also actually actively converse about their context. Like it is also useful for text generation, which is going to explain about the image as well as understanding the image to solve the particular different types of computer vision problems.